My name is Brian McConnell. I'm a software engineer. Started out my career working on telecommunications systems, and nowadays work a great deal with translation technology. I've also written 2 books about SETI and a number of scientific papers. My area of interest is mostly about what would happen if SETI detects an information-bearing signal. What would the sequence of events look like? And what types of people would be involved in the effort to analyze and comprehend the contents of such a transmission. So SETI, as you know, has been running for about 60 years, starting with experiments at the Green Bank Observatory. And is now more or less running continuously, looking for signals in both the radio and optical bands. There are groups at Berkeley, the telescopes in both hemispheres. Sorry, I'm getting a little bit nervous. And the people involved in these programs are, subject experts, radio astronomers and optical astronomers who are specifically working on searching for, artificial signals, operating at remote sites, often with limited connectivity. And, the SETI can basically be characterized as a project with a low probability of success, but if it succeeds, it'd be very high impact. A good analogy is an Earth impacting asteroid. It's very unlikely to happen in any given year, but if it does, would be very disruptive. So I'd just like everybody to imagine one day we wake up and one of these searches has found something, or it looks like something. This could be an artificial radio signal, or it could be an artificial optical signal. So, optical signals they search for are very brief nanosecond pulses that can briefly outshine the star behind them. Now, at first, we won't know that it's artificial, especially if it's a radio signal. One of the problems with radio SETI is that they detect millions of candidate signals all the time, but they're detecting our own technology. So discriminating between an actual alien signal and one of our own satellites or a ground-based transmitter is very difficult. And in fact, to date, we've had a couple of, I guess you could call dry runs, where we found something that looked like it could be an extraterrestrial signal, but it turned out to be human generated. So this process could unfold very quickly in some cases, or it could drag on for years in others. So a good example is the Breakthrough Listen Candidate 1 signal that was detected by the Parkes telescope. At first, it passed all the tests, looked like it was originating from outside the solar system, looked artificial, but it was a transient, was only observed once and for a relatively brief period of time. Or actually, it was observed on several runs, but it was only observed for a limited period of time and was only observed by one telescope. So that made it very difficult to confirm. So it looked like it could have been an extraterrestrial signal, but after a long period of analysis, the consensus is it's most likely human-generated signal. So in that situation, there could be a great deal of debate and discussion about is this really an alien signal or not, and it might never become agreed on. Another good example of a signal that meets those characteristics is the WOW signal that was picked up back in the 1970s. And on the other end of the spectrum, with the optical signal, that could be confirmed as extraterrestrial very quickly, perhaps in a matter of days. The reason for that is there's much less background interference to contend with, and that kind of signal is pretty unambiguous and doesn't look like anything we generate. So if you had a situation where one of the optical SETI programs detected a blinking pulse coming from a nearby star and observed it from 2 or more telescopes, you would know pretty quickly that we were looking at an alien signal. So at that point, once that's confirmed, that's about when the announcement goes out and the whole world is like, holy crap, oh my God, aliens. And then we proceed to the next step in understanding what we're looking at, and that's the signal analysis. What we want to know in this stage is the signal engineered to encode information? There are many ways to encode information on an artificial signal. So in the optical band, you can modulate the wavelength or color of the light. You can modulate the duration of each pulse. So for example, if you have 4 different pulse lengths, you could, encode 2 bits of information with the pulse duration. The interval between pulses, that's also something that can be modulated. And the polarization of the light. So, just with each pulse, you could probably pack 8 or 10 bits of information. And then, let's say you're pulsing 10 times a second, you can transmit 100 bits of information per second. Now, by our standards, that's a glacially slow communication channel, but that works out to several gigabits of information per year. So you could actually be receiving a decent amount of information. So at this stage of the process, the number of people involved would expand greatly. So anybody that's experienced in communication systems design, wireless communication and networking, anybody with that kind of expertise will be able to participate in this stage of the analysis and comprehension process. So it wouldn't just be SETI engineers at this point. You can imagine pretty much every electrical engineering department in the world would be interested in looking at this. And so and then the end product or the output, data product from this stage of the analysis pipeline is you basically start reading out signal states. Now you have no idea what these signal states represent. Maybe it's binary code, maybe it's something else. You have no idea how it's structured. Is it just one long sequence of signal states, or is it, are we looking at n-dimensional data structures? Could be anything. And this is where things get really interesting. Because once you start reading this data out, for one, it's not a huge amount of data. I mean, we're not going to be getting gigabits of data per second, at least at first. So you have a relatively small amount of data that can be distributed. And basically anybody with an internet connection and a computer and a hypothesis to test will be able to participate in this stage of the process. So, this would be a globally distributed effort to understand the contents of the transmission. It would involve both professional and citizen scientists. And one of the things that's interesting here, and this is, it's just an interesting thing with computer science in general, a lot of the most important contributions in CS, are the result of individual contributors or very small teams of people within larger organizations. So I like to cite the example of the Python programming language. It's widely used. It's used in some of the biggest, internet systems in operation. And Google, for example, is heavily dependent on Python. It was written by one guy, Guido van Rossum, in Holland back in the 1980s. So it's quite likely that most important contributions will come from people who are not involved in SETI, and it really could come from anywhere. It could be somebody within a university, could be this a random math whiz somewhere in South America. You just don't know, but that's what's interesting because there's so many things that you could we really have no idea what would be within the transmission in terms of content. So being able to try lots of different hypotheses, will enable us to speed up the process of understanding what's being sent if there's an intent to communicate. So what do we need in terms of information infrastructure to support this? Well, an interesting thing with SETI organizations is while they excel at processing huge amounts of data, petabytes and more, they're not set up to handle large numbers of users, because one of the things that will happen if there's a contact event is huge numbers of people will want information about, what have we found? What are they saying? What are their intents? So this system will have to, scale to handle millions of concurrent users. It'll need to be resistant to denial of service attacks because anything related to SETI will be a very attractive target for hackers. And it'll need to have what's called a revision history. So if one of the input sources to the system is corrupted or compromised, you can roll that back. And the operating cost should be minimal while the system is in standby mode, but then scale with usage. Now, the good news is there's several cloud-based services that meet most of these requirements. So if you were going to build it today, it'd probably look like some combination of Google Compute System or Amazon Web Services, and then there's source code repositories like GitHub that would work very well for this. So, I like to call this the Interstellar Communication Relay. And it's intended to be sort of, comparable in functionality to the deep space network, but largely based on cloud-based computing resources that are highly scalable and don't cost much to operate. So this system would, be intended to support, several different user communities. So, on one end of the spectrum, you'd have, highly technical people that were, signal processing experts that are looking for additional carriers or looking for additional modulation schemes. And then on the other end of the spectrum, you'd have less technical users, and they would be looking at derived data products. So, for example, imagine that there are uncompressed images or bitmaps interleaved in this transmission. And there's many different things that could be there. I'm not saying that there necessarily would be, but one of the things that would happen then is somebody somewhere would write a program to extract those images and convert them into a format that non-technical users can look at, so like PNG files, GIF files, that sort of thing. And so one of the other things that's interesting about this is as we start to understand the structure of the data and the different media types that might be represented, a broader community of people will be able to participate in the analysis process. So, imagine, again, if they're images, the images could represent anything. So you might have images of structures or buildings. So you can imagine archaeologists and other types of people looking at those images and trying to understand what they represent, and they wouldn't necessarily need to understand image processing software. So, and then I'd just like to wrap up with a few comments about risks. Originally, I was going to talk more in the front of this about the risks associated with SETI. A lot of people assume, or it's sort of widely assumed, that passive SETI or listening is a low-risk activity compared to transmitting. I would argue that's not true. Passive contact can be highly disruptive. John Traphagen gave a great talk here a couple of years ago about what happened when Commodore Perry sailed into the Tokyo harbor. The Japanese at that time had never seen steam-powered ships, and it upset the whole social order, because they realized everybody else, the rest of the world had advanced greatly over a period of several hundred years of isolation, and really caused a great deal of disruption to their society, and some would argue ultimately led to World War II. I think one of the big risks is that contact will attract a rogues gallery of con artists. About 30 or 40% of the population is already primed to believe that UFOs have visited us and aliens exist and have been here or are here. So there's going to be a huge audience of people who are going to be primed to believe people who present themselves as being ambassadors or otherwise somehow representing another civilization. There'll be a lot of money for those people to make, and there'll be a lot of people who will be happy to give them money. And this distinguished gentleman in the picture here, that's the Reverend Jim Jones from the People's Temple in San Francisco. He's been dead for quite a while now. He took about 800 people with him. And it's likely, I think, or almost certain, that there are people like him that will surface, in the wake of a contact event. And we need to be prepared for that. And one of the ways we can be prepared is to have adequate information infrastructure so that whatever we're receiving is comprehended as best it can, as quickly as it can, and that there's a trustworthy, reliable source of data that people can turn to, as well as the interpretation of that data. Well, no, Jim Jones, he led a cult. I'm just saying that, this kind of charismatic personality is, that's the type of thing that we're probably going to see is, people will surface that will, defraud people, create cults. And, especially if there's any ambiguity about the information we're receiving, people will be able to present themselves as having, special access to the aliens, or saying, hey, the government knows what's coming, but, they're not telling you, but I will. And there'll be a lot of people that will fall for that.
Thank you, Brian. We have several questions. First, what is SETI's policy if they think they found an ET signal? Do they notify/clear with government prior to public release?
So there is a protocol. It's voluntary, so it has no force in law. But all the SETI organizations, have signed on to this. So basically, they'll make every effort to verify that the signal is real, and then the team that made the discovery would make an announcement. Now, they're going to be very reluctant to jump the gun on that, because nobody wants to call a press conference saying, "Hey, we've made contact with aliens," and then 2 weeks later come back and about that signal from aliens. Well, we detected a microwave oven in our break room. So,
thank you. And finally, could spread spectrum broadcasts be distinguished from noise without knowing the details of the spectrum spread characteristics?
So I wouldn't know the answer to that question. I'm a software guy.
Copy that.
Thank you.
Good job. Thank you.